All right, and then for the fourth approach, bond energy approach, we need to make sure that we draw out the Lewis structures. If this was a free response question, part A or B would probably be to draw out that Lewis structure. So make sure you review how to draw out Lewis structures. So it says, using the following structures and bond enthalpies, calculate the delta H of reaction, so the enthalpy of reaction, and compare the result that you found in part A and explain any differences. So we have SO2, that was one of our reactants, and we had two of them, and we had two SO3s, that was our product. And then oxygen, we had one O2, that was one of our products as well, one of our reactants as well. So our reactants need to be broken and our products need to form, right? We need to break down our reactants in order to form our products. We had two reactants, so we need to break both of those. So we are going to break the SO2, and we are going to break the O2, right? And if we look at SO2 right here, we have 1, 2 SO bonds, right? We have 2 SO double bonds, right? Which is that right there. And so we're going to break a total of, because we had 2 SO2s, so that means we're going to break 2 of these, right? So we have 1, 2, 3, 4, because we had 2 molecules of the same thing. So we need to break in total 4 SO bonds. And we only need to break 1 oxygen, so we only need to break 1 OO bond. Right, and so when we multiply this out, we have 4 times the 522, and we have 1 times the 495. All right, on our product side, we needed to form SO3, and we had 2 of these. Remember, we had 2 SO3s, so we have 1, 2, 3 for the first molecule, and then we have 1, 2, 3 for the second molecule. So in total, we have 6 of those. So we had 6 SO bonds for our product. And so for that one, we're going to multiply it by 6. And our SO is still 522. All right. We need to make sure we have positive and negative signs associated with each of these. If you're breaking it, you have to put energy into it in order to break it. So breaking is positive. If you're forming it, you're taking energy out in order to form it. And so forming will be negative. Breaking will always be positive. Forming will always be negative. So we have positive 4 times 522. Multiply that out. We should get 2,088. 1 times 495 should give you 495. And then negative 6 times 522 should give you negative 3,132. We're going to add all 3 of those together. And when you add all 3 of those together, you get the delta H of our reaction. So the delta H of our reaction should be negative 549, 49 kilojoules per mole. Right? That is our delta H of reaction, our enthalpy of a reaction using the bond energy approach. It can kind of be like Hess's law, where you're adding them together to figure out like what the overall is. But it is very different. Bond energies are averages, and it does not take into account interparticle or intermolecular forces. And so you want to also include any resonance structures that might form. And so the bond energies overall, whenever you're using the bond energy approach, they're not as accurate as the top 3 approaches. So Hess's law, products minus reactants, and then experimental approaches. So that's the difference between the negative 198 from A versus the negative 549 kilojoules per mole for D. So it's not as accurate as the top 3. And then the last part, it says draw the graph of the potential energy versus internuclear distance for both SO and OO bonds to show why the bond energy for SO is greater than that of OO. So for this one right here, we're then going to go ahead and draw 2 different ones. I'll do blue for SO, and I'll do green for OO. And so for SO, the bond energy is greater. It's 522 kilojoules per mole, right? The bond energy for SO is right here. The internuclear distance, so potential energy will be our y-axis, and then the distance will be our x-axis. For sulfur and oxygen, it will kind of look something like this. And then for oxygen and oxygen, it's a little easier to break, right? It's 495, and so it's going to be a little bit shorter, like that, right? So the oxygen will be a little bit shorter, the sulfur and the oxygen will be a little bit bigger because it's harder to break. And so the energy is going to dip down further for sulfur, right? Because there's more energy that needs to break it, whereas for oxygen, it's not as much energy. So the potential energy, well, represents the ideal separation between the two nuclei that maximizes the attractions and minimizes repulsions. So oxygen has a shorter bond because they're smaller atoms, and sulfur is a little bit bigger of an atom, so it has a bigger bond, or a longer bond. So if I were to draw that out representationally, right, sulfur to oxygen, because sulfur is a little bit bigger of an atom, oxygen is a little bit of a smaller atom, versus two oxygens. It's going to have a little bit of a shorter bond because they're smaller atoms. And then therefore it has a higher well because it has smaller bond energy, right? There's a really good PhET simulation that I can show you guys in class to explain the potential energy graphs a little bit better. I would read through the teacher edition notes and kind of wrap your mind around it and write down any questions that you might have for that graph right there.